Human rights matter, but conversations about rights can be polarizing, confusing, and frustrating. Lawyers Claudia Flores and Tom Ginsberg have traveled the world getting into the weeds of global human rights debates. On Entitled, a new podcast from the University of Chicago Podcast Network, they use that expertise to explore the stories and thorny questions around why rights matter and what's the matter with rights. Subscribe to Entitled, part of the award-winning University of Chicago Podcast Network.
So, Shalma, as you know, if you dig through all the pages of the physics journals, this year, last year, 10 years ago, 50 years ago, whatever, you're going to find, practically countless number of different ideas that have been proposed for various solutions to problems that theoretical physicists have pondered, and basically new proposals for kinds of physics that might at least hypothetically exist in our universe.
Basically, there's a shitload of papers out there.
There is a shitload of papers on a shitload of different ideas. But even though none of these ideas, or pretty much none of these ideas, have been experimentally confirmed, we don't think they're all equally likely. There are some that we think are really ad hoc and long shots and probably have nothing to do with anything. And then there are some that maybe can solve a couple of problems that we think are important problems to solve. And then maybe those theories we think are a little more likely. And then there are some that, for a confluence of different reasons, we think are super promising and well motivated, and maybe even are actively likely to be part of the laws of physics. All right, so I did this experiment to kind of get an idea of which ideas in theoretical physics particle physicists are really excited about. So I went to this preprint server and I searched for certain words that might appear in titles. So of course this doesn't get every paper, because you write papers sometimes about things without using that word in the title, but it gives you some idea. So I started out by looking for the word axion or axions in the title. This is the thing you're working on, Shalma, as of course you know. And there are about 2,500 papers on the server and on that topic, which is a lot.
From all time?
Yeah.
That is a lot. Wouldn't be able to read all of those.
No, not even close.
But at the same time, it's not that huge of a number either.
I would think 2,500 is a very popular idea, but not the most popular idea.
Right.
So the next one I tried was the word grand, which might appear in grand unified theories or things like this. And the number there was a little bit smaller, about 1,900.
Oh, wow. So less.
Yeah, less. Now, this is imperfect because you could imagine lots of papers being on these topics without these words in the title, but they give you some idea. So then I tried inflation, as in cosmic inflation, and there were about 6,700 there, so way more. So that seems to have more papers about it. And then I tried string or strings, and I got about 13,000. So far, that's the most popular idea. But then of all the new kind of ideas and theories that have been put out there, the one that seems to have the biggest number is supersymmetry. So when I searched the Inspire database for papers with supersymmetry or supersymmetric in the title, I found almost 20,000. So way more than all of these others. Well, almost more than all these others put together. It's by far dominated the theoretical physics landscape since its conception, 4 decades ago or something.
So how does a theory get so popular before there's even any experimental evidence for it? And are physicists still paying as much attention to supersymmetry today as they once were? We'll get to all that and more in today's episode, so stick around. And before we get started, just a reminder that if you like our show and you want to support us, our Patreon is now online, where you'll get access to exclusive Ask Me Anything episodes where you can submit questions, and you'll get a free Why This Universe sticker, and most importantly, our very deep appreciation. So you can find our Patreon at patreon.com/whythisuniverse. And our raffle is still happening. So for 2 more weeks, we're collecting entries into a raffle to win a signed copy of Dan's new book, At the Edge of Time, Exploring the Mysteries of Our Universe's First Seconds. And so you can enter our raffle by either joining us on Patreon or by tweeting at us at WhyThisUniverse with a screenshot or picture of you listening to our show. With that, let's get into it. You're listening to Why This Universe, a podcast where we break down the biggest ideas in physics. My name is Shalma, and I'm a PhD student at NYU.
And I'm Dan Hooper. I'm a theoretical astrophysicist at Fermilab and at the University of Chicago. So when I think back to when I was a grad student in the early 2000s, if you had gone to some particle theory or particle physics conference and just asked around what do people think of supersymmetry, it would have been like a pretty uniform opinion that supersymmetry probably exists in nature. It's probably true. Now, they all agreed that it hadn't been tested yet and they weren't certain, but I think most of these people would have been surprised to find out supersymmetry doesn't exist. And I was one of them. I mean, I wasn't certain by any means, but I wrote papers on supersymmetry because I found it to be compelling. I even wrote a book about supersymmetry that was published in 2008 called Nature's Blueprint. And in that book, I said that I thought there was like a 50-50 chance that supersymmetry was real, which might not sound super confident, but
for an untested theory, that's pretty high.
It's pretty high. I mean, how many things that you have never seen any evidence for that you're 50% sure are true,
Yeah. So you probably want to know at this point, what exactly is supersymmetry? So let's back up a bit.
So supersymmetry is an idea or a theory that relates the particles we call bosons to the particles we call fermions. So bosons and fermions are just different classifications of particles that have to do with how much they spin, how much angular momentum they have. All particles are either a fermion or a boson. So fermions are kind of the particles we think of as matter, particles like electrons and quarks and neutrinos. All of these things are fermions. And bosons are the particles we usually think of as force carriers. So like the photon, the gluon, the W and the Z bosons that communicate the weak force. These are all bosonic particles or bosons.
And fermions and bosons, the reason the names are so weird is just because they're named after two guys.
Yeah, I mean, Enrico Fermi and Bose.
They each got one type.
They each got one. They figured out the quantum statistics of different kinds of particles back in the early 20th century, and that's where it comes from, yeah. The main idea of supersymmetry, which goes back to the early 1970s, was you could construct particle physics theories where there was a symmetry, what we call supersymmetry, built into the laws of physics that said for every fermion that exists, there had to exist a corresponding boson with all the same kind of properties, but being a boson instead of a fermion and vice versa.
So, for example, the electron, a fermion, has a bosonic superpartner called the selectron, and each quark has a superpartner squark, and so on. So, for the most part, all of the bosonic superpartners are named by adding an S at the beginning of its fermion's name, which stands for super. So, it's not too bad for the top quark and its corresponding stop squark, but it gets pretty ridiculous once you get to the bottom quark. Spottom squark. And the fermionic partners to the bosons are named by adding eno at the end. So the Higgs boson has a fermionic superpartner called the Higgsino. It's kind of cute.
So my wife Cheryl, her favorite particle in all of theoretical physics is the smuon. I'll just throw that in. She's always been enamored by that name. And yes, let's just concede that the naming convention of superparticles is pretty ridiculous. So this originated as an idea in the Soviet Union. So I'm going to try to pronounce the names of these Soviet physicists, but if I get them wrong, I apologize. But Yevgeny Lichtman and Yuri Gofland, they proposed this idea in 1971. And you should think of these people as like deeply mathematical physicists. And they basically said where you can construct these theories and they have these neat mathematical properties, or maybe profound depending on your outlook. But you can't have a fermion without a boson. You can't have a boson without a fermion. That was kind of built into the structure of this theory. So then in 1972, a second version of supersymmetry was invented by these two other Soviet mathematical physicists, Dmitry Volkov and Vladimir Akulov. And basically it stayed out of the hands of Western physicists during this time because there wasn't a lot of communication between the Soviet scientific community and the, Western European or American or Canadian, for that matter, scientific communities. There just wasn't a lot of back and forth. Journals weren't usually translated. They didn't go to the same conferences very often. And even when those papers were translated and things like this, like oftentimes they just didn't understand why certain ideas were exciting or important. They didn't, unless you're really embedded in the same community, you just might not get it, what the other side's doing. So even though scientists in the West weren't aware of what these Soviet physicists had done, there's something about supersymmetry that just was kind of in the water at the time. And a few years later, two Western physicists invented the same basic idea. This is Bruno Zumino and Julius Wess, both in Western Europe at the time. And it kind of just grew and grew and grew in interest. And people thought this mathematical structure was really, really appealing. And what really confuses me when I look back at this is why so many people thought this was so compelling in the 1970s, because I don't get it. I don't get it. If somebody proposed a physical theory where if you replaced all the trees in the universe with cars and all the cars with trees and nothing would be changed, I'd go, well, okay, fine, you can write that down, but who cares? What does that have to do with anything? There doesn't seem to be any relationship between bosons and fermions in the universe that we've ever observed in any experiment. I'm at a total loss about why this was seen by so many people to be so compelling, at least at that point in history.
Especially because this kind of theory, the supersymmetry idea, means that there are tons of particles that exist, like all these extra bosons that we just haven't seen and all these extra fermions that we've never seen that are the partners to the other ones. And that's a lot of like mysterious, just like particles that we haven't seen.
It's a lot to postulate if you don't have a good reason to do it, right? If supersymmetry is true, then every fermion, like say an electron, has a corresponding boson, which we call the selectron or superelectron. But we've never seen a superelectron. We've never seen a selectron. Similarly, the photon has to have its fermionic counterpart, which we call a photino. Never seen one. So this is a lot to, suppose exists, unless you have a really good reason. If I had to guess why people thought it was so compelling early on, it has to do with the kind of unique nature of supersymmetry. So in 1967, Sidney Coleman and Jeffrey Mandula, these legendary physicists, proved a theorem that basically showed that any symmetries that you can find in realistic theories of physics had to be either a symmetry of space and time or what we call an internal symmetry. So symmetries of space and time are things like you can translate things in space or time or rotate them, and basically everything's left unchanged. Through Noether's theorem, which we talked about in a recent episode, this basically comes down to things like the conservation of energy, the conservation of momentum, stuff like this. The internal symmetries are things like gauge symmetries, which we also recently talked about in the Noether's theorem episode. And these symmetries are related to things like the conservation of electric charge. So what Coleman and Mandula proved is you could have symmetries that were space-time symmetries, or you could have symmetries that were internal, but they couldn't be both. There were no combinations of these symmetries. But it turns out there's an important loophole in this theorem, which supersymmetry is the one counterexample to. So for very technical reasons that I don't think we can get into here, supersymmetry allows you to break the Coleman-Mandula theorem because it is both a symmetry that has to do with angular momentum, which is a space-time symmetry, and it's a symmetry that has to do with the internal properties of particles. It's an internal symmetry too. So supersymmetry does seem to be special in a certain mathematical way from this perspective. So I don't know, if you were trying to judge different theories that were all untested, you might think the unique one is something special, something to investigate more. I'm not sure if I agree with that, but you can at least understand why some people might think that. But then slowly, starting in the early 1980s and then building to the present day, physicists started to find reasons to think that supersymmetry might be real in nature. Reasons that didn't just have to do with mathematical elegance or uniqueness or something, but it began to be appreciated that supersymmetry could solve certain problems that were plaguing theoretical physics at the time.
This is so surprising to me because I always thought that these problems came first and then supersymmetry came up as this like brilliant solution to all of these. But you're saying that supersymmetry was just like in the air, people were interested in it, and then they were finding all these special things it could do.
My guess is if it didn't solve all these problems, I might never have heard of it. It might have been like an esoteric idea from the 70s that some mathematicians thought about once. And like maybe it would have never been a big deal for people like me and yourself. But it was interesting enough mathematically to like get it off the ground. And then it was appreciated by a bunch of smart people that you could solve this problem and that problem and do this. And oh, look, this feature, it solves this thing we didn't even know about yet, et cetera. And all this built up momentum for people to take supersymmetry as an increasingly, likely, feature of nature.
So let's talk about these open problems in physics that supersymmetry could explain away if it's true. And these aren't just little things. To this day, these are some of the biggest and deepest open problems in physics.
So the 20th century produced two of the most spectacularly successful theories in the history of science. So on the one hand, there's Einstein's theory of general relativity, which is a theory of space and time and gravity. And on the other hand, there's the theory of quantum physics, or quantum field theory in its modern form. And this is a theory of the other forces and matter and energy and the forms that they take. Both of these theories have been tested with hyper high precision in any number of different ways, and they keep making predictions that agree with experiments and measurements. So, like, that's what you want your physical theories to do. But it's been appreciated for a long time that if you try to make a single theory that incorporates both general relativity and quantum field theory in a self-consistent way, well, it just doesn't work. One or both of these theories is broken in some important way, and we don't know how. Ultimately, we hope to write down a successful theory of quantum gravity, one that combines these two theories, but we've never been able to do it. So by the early 80s, it started to be clear to people who are working on quantum gravity theories that it seemed to be a lot easier to make these theories of quantum gravity, especially string theory, work if nature were supersymmetric. If there's this supersymmetry imposed on the nature of space and time and the particles that exist in the universe, then you can write down string theories that can explain the sort of phenomena we have in our universe without having mathematical inconsistencies and infinities arise and things like this. So basically, if you want to use something like string theory as a theory of everything, as a theory of gravity in space and time and a theory of matter and force and energy, then you need to have supersymmetry built into nature. And around the same time, other theoretical physicists were fixated on these theories that are known as grand unified theories. So whereas theories of quantum gravity are trying to combine the quantum forces we know of that are part of the standard model with gravity and general relativity, the grand unified theories are trying to take the three forces in the standard model, electromagnetism and the strong and weak nuclear forces, and explain them in a kind of unified package. So if a grand unified theory is true, then these three forces are really different manifestations of one overarching grand unified force. We should think of electromagnetism and the strong and weak forces as all being part of the same thing in the same sort of way that we think of electricity and magnetism as being part of the same underlying phenomena today. So, this could be very powerful and very exciting. And I would still say today, most physicists, most theoretical physicists think there is probably some sort of grand unified theory built into nature, but we don't know how to test it. And we have lots of ideas for how this might work. So the real challenge in getting a grand unified theory to work is that when you look at the three forces it's trying to describe, they don't look particularly alike. The strong force is a lot stronger than the other forces. The electromagnetic force is mediated by a massless photon, and the weak force is mediated by heavy W and Z bosons. Like, it just looks like three very different kinds of forces. In particular, the three forces have these three different strengths that seem unrelated to each other. And if you wanted to have a grand unified theory to work, those three forces should really all have the same strength. But it turns out that the strength of a given force can change or evolve depending on what temperature it's acting at. So as you look at the three forces of the standard model and ask how strong were they when the universe was 1 billion degrees or 1 trillion degrees or a quadrillion degrees, whatever, you see that those three forces get closer and closer to each other in strength, giving you hopes that maybe at some very high energy scale, some very high temperature, they could all have the same strength and be part of a grand unified force under those conditions. So if you do this calculation in the standard model, you don't get the answer you'd want. The three forces kind of get in the same ballpark of strength, but they don't all unify to a common value. But it was appreciated around this time and confirmed in experimental in particle accelerators in the early 90s that if you had supersymmetry, so you had all those extra particles that supersymmetry predicts, and those particles aren't too heavy, then these temperatures, or these forces, their strengths, will evolve with temperature in a way where they all come to meet at a common value at an exceedingly high temperature of about 10 to the 15 GeV. So this is a tiny, tiny fraction of a second after the Big Bang. But it seems like you could make a grand unified theory work if nature is supersymmetric.
The problem is the temperature where those three forces would have the same strength is enormous. And there's really no way to imagine building an experiment that could get that hot. And so we can't really test supersymmetry or grand unified theories this way. But if it's true, it means another big feat for supersymmetry.
All right, so by now you should start to be getting a sense for why physicists liked supersymmetry so much. You have this potential help with solving the problem of quantum gravity. You could make grand unified theories work. These are things that physicists wanted to be true and wanted help resolving, and supersymmetry seemed to be very helpful in these regards. But in my opinion, the strongest argument in favor of supersymmetry has to do with what we call the hierarchy problem. So we talked about the hierarchy problem in last episode of this podcast. And I'll just kind of remind you, if you didn't catch that one or need a refresher, the idea is that particles, both fermions and bosons, interact with the Higgs boson in a way to contribute to its mass. And if you just take the standard model and calculate this, it turns out that the Higgs should be wildly heavier than we observe it to be at the Large Hadron Collider, by a huge factor. So something has to happen to explain why the Higgs is so light, at least compared to our expectations. And it turns out supersymmetry just does that all on its own. Because in supersymmetry, there's a boson for every fermion, and these both contribute in the same way to the Higgs, allowing their contributions to cancel. So you can think of the fermions giving us a positive contribution, the bosons giving us a negative contribution. And since they're related by the symmetries of supersymmetry, they pull kind of in equal strengths in opposite directions, leaving the mass of the Higgs relatively light. And it's hard to put, enough emphasis, or it would be hard to put too much emphasis on how big a deal the hierarchy problem has been. A lot of ink has been spilled trying to find explanations or solutions to the hierarchy problem. We have a bunch of ideas, but frankly, supersymmetry is by far the cleanest and simplest explanation for why the Higgs is so light. And I think that has driven a lot of the conversation around supersymmetry. So in addition to the role that supersymmetry could potentially play in the problem of quantum gravity, in building grand unified theories, and in solving the hierarchy problem, it could also potentially provide a solution to a problem that's really close to my heart, the problem of dark matter. So it turns out that in most viable theories of supersymmetry, the lightest of all the superpartner particles turns out to be stable.
So when we say a particle is stable, what we mean is that it never decays. So it turns out most particles actually have a finite lifetime, after which they are expected to decay into lighter particles. But having a stable supersymmetric particle is super important, because in order for a particle to be a dark matter candidate, it has to be stable.
And maybe that particle will be weakly interacting and not electrically charged and not strongly interacting or anything like this. And then, this lightest superpartner could be a WIMP, a dark matter candidate. And they could have been produced in the early universe in the right abundance and basically solve all the problems that we want in a viable explanation for all the evidence we have for dark matter. So when I look at all this information in aggregate, you can see how somebody would get excited about supersymmetry. So, going back to when I was in grad school, early 2000s, I was taught by my professors, and I read in these review articles that, without supersymmetry, you have this problem, and nothing seems to make sense. It's a hopeless confusion. But if supersymmetry exists, then now we understand the Higgs, we understand grand unified theories. You understand how we go about using string theory to build a theory of quantum gravity. It all just kind of fits together. And we all kind of thought this was going to be the right answer. And at the time, we were really excited about this particle accelerator called LEP, or LEP-2 at the time, which was going on at CERN. It's a big electron-positron collider. And I just remember month after month, there would be these new results. And we were on the edge of our seat to see, did they discover the first superparticles? And they didn't. And as a side note, I'll mention that if LEP had just had a little bit more energy, 10% more than it had, it could have discovered the Higgs boson, more than 10 years before the Large Hadron Collider did. But of course, we didn't know that. We didn't know how heavy the Higgs was going to be, and we had to wait for the Large Hadron Collider to make that discovery.
Yeah, that would have saved us a lot of money, huh?
Oh, I think you'd still want to do the Large Hadron Collider for a lot of other reasons.
I'm kidding. Yeah.
But would have saved a lot of physicists, in that 10 years, a lot of papers were written about guesses about what the Higgs might be like and things like this. We would have saved a lot of effort if we had made that discovery a decade earlier. So electron-positron colliders like LEP have a lot of big advantages. The data they produce is pretty clean and it's easy to interpret. But they don't generally accelerate the particles to particularly high energies, at least not as high as you can accelerate protons to. So, for example, around the same time as LEP, the Fermilab Tevatron was accelerating protons and antiprotons to about 20 times as much energy as LEP was able to do. And the Large Hadron Collider, which accelerates protons, they're able to accelerate those protons to 60 times more energy than the LEP's electrons and positrons had. So what that means is that whereas LEP was really good at looking for relatively light particles cleanly, the Large Hadron Collider is really good at looking for very strongly interacting heavy particles. And when it comes to supersymmetry, that means the squarks and gluinos, the superpartners of the quarks and gluons, are the best target, or at least probably the best target. So we fully expected the Large Hadron Collider, or at least a lot of us did, to discover squarks and gluinos if they existed. They should be produced at a huge rate, and they should decay really quickly into these distinctive signals, including a bunch of things like, big jets of quarks and maybe tracks of other kinds of particles and stuff we call missing energy, which is basically those dark matter particles escaping from the detector, and you don't see them, but you notice that the momentum's all pushed to one direction and allowing you to infer that something must have gone in that other direction. So when you take all this together, there was, good reason to think the Large Hadron Collider should be a great machine to discover things like squarks and gluinos. But so far, the LHC has collided about, 40 quadrillion pairs of protons. So not a small amount of data they've accumulated. And over the course of this time, they produced something like 8 million Higgs bosons, distributed across 300 petabytes of data. It's not like this machine has just started or something. But still, they haven't seen any squarks. They haven't seen any gluinos. They haven't seen any evidence of supersymmetry, that's worth even talking about. So, what are we supposed to think about this? When I wrote that book on supersymmetry, Nature's Blueprint, back in 2008, I wrote in that I thought there was about a 50-50 chance that supersymmetry actually exists in nature. And I said, if it does, the Large Hadron Collider would probably discover it. So, what's the chance now? It's certainly smaller than that, but it's not zero. Maybe it's 1 in 4 in my best estimation or something.
Wow, that's pretty optimistic still.
Yeah, I think all those reasons to find supersymmetry compelling are still pretty compelling. They aren't proof, but I guess I'm a little bit old school in this sense. But if you went to a physics conference and you asked a bunch of different people, you get a lot of different answers. There is no consensus. Some people will say, 70% likely. Some will say 0.1% likely, and everything in between probably. It's a huge diversity of opinion. But where we do all agree, though, is that this will be settled by data. So I'm really excited about more data from the Large Hadron Collider, more collisions. In the future, they're going to do something called the high luminosity upgrade, which will allow them to study about 10 times as many collisions as the current configuration can do. And maybe beyond that, they might even have an energy upgrade where they can make those protons go even faster and collide at higher energies. And this will only make the Large Hadron Collider better at looking for supersymmetry and other kinds of new physics. So ultimately, we will find out one way or the other if supersymmetry exists. And it won't come down to anybody's opinion about what's elegant or what mathematics looks compelling. It will come down to what the data say.
What would it take for you to be convinced that supersymmetry is wrong?
Any kind of supersymmetry that will address things like the hierarchy problem and the problem faced by grand unified theories predicts that there should be the superparticles at a kind of modest mass, somewhere around the tera-electron volt scale, roughly. And the longer the Large Hadron Collider runs, the higher the limits on different particle masses become. So right now, we know from the Large Hadron Collider that if squarks and gluinos exist, they have to be heavier than a couple of tera-electron volts, a couple of TeV. If they did a high luminosity run and that number went farther up, it would make it harder for people to think supersymmetry really solves these problems. And if they did an energy upgrade and maybe went from a couple of TeV to 4 TeV or 5 TeV, and you didn't see anything, I think very few people would continue to think supersymmetry is the answer to these puzzles.
So physicists are still looking for supersymmetry today, and the longer we go without evidence, even with better and better experiments, the harder it will be to maintain faith in the theory, even if it is super compelling, and even if we'd have to miss out on a particle called a smuon. Thanks for listening to Why This Universe. As a reminder, our Patreon is now up on patreon.com/whythisuniverse. If you want to support us more and get access to some exclusive content and a free sticker. And remember, it also enters you in a raffle to win a signed copy of one of Dan's books. And you can also enter for free by tweeting at us with a picture of you listening to one of our episodes. Thank you so much for your support. Our show is produced and edited by me, Shalma Wegsman, co-hosted by Professor Dan Hooper of the University of Chicago and Fermilab, and all music is produced by Jake Kleinbaum. Why This Universe is brought to you by the University of Chicago Podcast Network.